Yeah, so very good evening to everybody. I hope you are having a good week. Okay, so what we're going to do is continue
Some
with,
nice weather, at least two
yeah,
digits, which is good, right, Professor?
what is it?
Some nice weather we have in the double
I
digits.
agree. I agree. I agree. Although, I mean, now we are having to face the aftermath of, you know, a little bit, puddles of water when you walk on the streets, right? Yeah, I think it's better weather now. So I hope everybody's mood is also better.
Ready
So
for spring.
I know, I know. Um, Okay, I think by the time we finish this course, surely we'll be beyond spring, hopefully, and we'll be in much better weather. Yeah. So okay, so I just wanted to, again do a little bit of logistical, take a couple of logistical points right now, and then get back to where we were working last time, where we stopped last time, which is about Word2Vec or in general embeddings for words. So. Um, let's start with projects. Okay, so project, I know, right now, by this is second assignment, so I hope you have your teams frozen pretty much and have some good work balance. So project intermediate report, which is basically like a proposal. If you think about it, it's just a proposal of what you promised to do in the next let's say 6 odd weeks. So that is due next week, in about 6 days. And then I've also set up time slots for me to meet each of the teams um, next, during the class hours. So we will not have a regular scheduled lecture session, but but we will have 1:1 meetings with each team. So that was quite valuable last time, or in the previous sessions, previous iterations of this course. So do come prepared to ask questions about feasibility or even technical questions, and we can discuss things. And in fact, of course, the important thing for this touch point is for you to inform me or the teaching staff on where you are in terms of what you want to do with the project, how much you have done initial preliminary work, and also what you plan to do in the next 6 weeks. Okay, so this is the link. It's the same link, if I recall. There's the same link where your names are there, team member names are there. So you can see one of the columns has time slots. So adhere to those time slots and use the Zoom link that's written on the Excel sheet. Okay. Um, if you have any questions about this logistic, just let me know. So is this clear? So next week it's just going to be a little bit non-standard stuff, in the sense it's not going to be a regular lecture session. It's going to be 15-minute meeting with each 15 minutes of meeting with each team. So there are quite a few teams, so that's why it's only 15 minutes. But um, otherwise, this touch point is right after you submit your intermediate report. So it's like you should have fresh context on what you submitted as your proposal, basically, or the intermediate report, and therefore we can discuss more on it. And I'll also get a chance to look at the reports by that afternoon. Um, One important thing that's not explicitly listed in the project instructions is that you should try to create, let's say, one slide of some sort of a project management plan, in the sense that who's going to work on what, and you know how are you going to pace yourself for the next few weeks to be able to get to the project to a concluded state, right? So this is just an extra ask that which was something that I also informed in my previous iterations. It's just that I didn't list it in the project instructions, but it's just something. It's not a final deliverable, right? It's basically for me to know how you're going to pace yourself for the next few weeks in terms of different steps that you want to perform in your project, and who's going to do what as well. Because you have, you are a team, so you want to split tasks and work together. Any questions about this part? Okay.
Report
Yeah.
will be submitted on the blackboard, but for the slide, you're expecting us to have it in class, like when we meet.
Yeah,
Think
yeah. That's what I think would be easier. Yeah, I mean, we'll just share this. I mean, slide is just a common denominator, a common format. Yeah, yeah.
Awesome.
I'll just want to maybe even it'll be good if one of you show the slide when we are discussing the project in the next week in the 1:1s.
So, Professor, I have a question. So I'm assuming we can get the proposal down. Let's
Yeah,
say a month from now, it turns out that either
yeah,
our project is way too big and we're
yeah,
not going to be able to do it, or it just turns out to be
yeah,
kind of too simple and too trivial.
yeah.
How do we what would we do at that point? You know?
That's a great question, John. And in fact, the touch up is for extra pair of eyes to kind of estimate whether it's too trivial or too ambitious. Um, so hopefully that will catch potentially these two issues. But still, there's a chance that after we you talk to us or the teaching staff next week, you or the teams, there is still a chance that later on something could be too ambitious. So I would say while building the proposal, you should have different degrees of outcomes. So there could be something. So sometimes some projects could be mostly reproducing starting from a starter code base from maybe GitHub or some research code base, for example, from papers with code. So that could be one baseline that's not ambitious, right? I mean, reproducing something where much of the code is written and you're just trying to poke around and do diagnostics on it is for example one level. And then you can say, hey, the next stage which we want to clear is this, and maybe some of these more, I guess, ambitious stages you may not be able to get to depending on your time as well as your skills and things like that. So that's fine. So I would say plan properly so that you have that uncertainty built into your what you're planning to deliver. So you can
Okay.
deliver some of the surefire things, and then maybe the more risky things you can drop if needed. Yeah.
All right. Thanks.
Yeah, that's a good question. So, project management, by the way, I mean, so some of you who might have more experience in project management might be maybe thinking this is too simplistic, but for me, so for us in this course, it's not so much that we have to follow a very rigorous, project management plan. It's just the slide that I was asking for next week is just, you can do it in any way. You can, some folks even do Gantt charts, but it's up to you how you want to think about timelines and your bandwidth, right? You only have X number of hours per week for this course, and so and between you, whatever is the total number of hours, you need to kind of plan for each task, okay, properly. Okay, so next, so if any other questions about the project? uh,
So, Professor, quick question, it's Chaitanya. So, for the
mhm.
project plan, a normal PPT slide would be good enough, right? Like we can
No,
do
no, no,
a
no. The project plan itself, I think there's some instructions on the website, right? Also on the project instructions page, right? Let me
okay, okay. So,
see.
yeah,
I
I'll
mean,
look for the proposal. I haven't taken a look.
yeah,
Previously, I think proposal part was in there, but I'll take a look at it.
yeah. I mean, see, anyway, at the end of the day, so recall that so whatever you do, I would say that material you would like to reuse it. So certainly, if you make a deck that's acceptable, I'm not sure. I mean, because in the sense that it will hopefully you'll reuse it for your final presentation. But I think the project instruction says you should write something, and that's because you can reuse the same thing for your reuse, as in it's just going to be extended when you submit your final version, for example, right? A proposal can be easily modified to actually doing the works that you claim in the proposal. So don't do things which are not useful. So certainly deck is useful because you will make a presentation, but the thing that will be evaluated is the report, right, at the
Okay,
end of come March, first week of March.
okay.
So the report is the most critical thing. The slide deck is mostly for for example, eventually when you present, that will be useful.
Oh, yeah, makes sense. Thank you.
Okay, good. So let me move on to quickly getting a feedback on the second assignment experience. Uh, I mean, I will not take feedback in real time right now, but what I wanted to say was that there were two questions, and many of you have tried, and many of you have faced a lot of hurdles while dealing with both the first question and the second question. It's natural, so don't feel that just because you face a lot of friction or trying to understand or trying to work with some code base that it's super difficult or anything. I mean, it's just that's that friction is expected, especially for first question. uh, you know because there was an ants versus bees example, right? One, I guess, path could have been to try to replicate your data set to be exactly in similar folder, right? There was a train folder and validation folder for that ant and bees example. So you could have put your CIFAR10 data in that way manually, potentially, and then hopefully the code would have been similar. If not, you would have had to fiddle with what are called data loaders and data sets. You don't have to even, so data loaders and data sets from the Torch package or Torch Vision package. But you don't even have to do that. You can actually very manually also handle your data, your CIFAR10 data. You can literally iterate through file names, read the image in that batch, for example, and pass it through the model for a forward, for a backdrop step. So there are many ways to do it. I hope, I mean, the example, of course, was grounded in trying to use data loaders and data sets. And there's a particular pattern in that example. But I hope that, folks who, found that example difficult, it's not the only way to do it. So if you have prior experience in ML, doing training in a slightly different way, that's totally fine. Writing your own from scratch stuff is fine. It's just that working with images, as you have already seen, is a little bit tricky. And so learning these extra helper objects may pay off in the long run. Okay, so by the end of assignment 2, so which we have finished, I hope you're a little bit more familiar with, if you have gone the route of data sets and data loaders, I hope you have a sense of what they're trying to do. Okay, they're just trying to help you create a batch easily. And then once you get a batch of label, inputs and outputs, then you just work with, and then the rest of it is very similar to what you'd see in any ML step. Okay. And the second thing is, I hope you've seen the explicit, I hope through that CNN example, you've seen an explicit example of, again, doing gradient descent, okay, which is literally in that, in each epoch, you're basically getting a batch. And once you get a batch, you're doing a forward pass, getting the loss value, and then doing a backward step to get the gradients. And then you're doing a gradient update, right? So I hope that pattern, which you saw even in assignment 1, and of course, the more early on sessions, that's exactly how you would do it, even in future in any other model as well. And the cool thing is, since you work through assignment 2's, the CNN example, many models that you might have worked on with packages, let's say random forest base, from some package, or XGBoost package, let's say, or many other models like SVM, model from some other package in R or Python or whatever, they hide this optimization step, right? So there is a pattern in scikit-learn as well as in other packages that says model.fit, right? Model.fit, and you give x's and y's, and it just does something, right? And updates the weights essentially. That model.fit is essentially the train step. So now we are actually looking at the full bare bones, gradient updates and changing of weights from something to something to something to something, eventually converging to hopefully good weights. That's exactly what model.fit would have done. But knowing this level of transparent details of what goes on when something like model.fit is called is a good exercise. Okay. So of course, second question was a little bit non-standard. There was no neural networks. I mean, there was some amount of ideas from neural networks in the sense that eventually you wanted to get embeddings. These are the V1 to Vm vectors, right, of your choice, whatever the choice of dimensionality, 10 dimensions, 5 dimensions. You wanted to get embeddings for movies, okay? And you have the raw data, which is the Xij, which is the counts of counts of users who have seen 2 movies, INJ together, common count. So there's not, although there's no neural network explicitly, there's no hidden layer and stuff like that. But you can, use what you saw, or at least the motivation for that question was to see that, hey, there's a loss function. This looks like squared loss. And there's some parameters. This is V1 to Vm, which are whatever is the number of dimensions you want to pick. And I just need to pick these vectors. Okay. And hopefully the ideas from last time's Word2Vec, or in general, vector encoding of words, hopefully helped. If not, it's okay. But that was the objective of that question. Okay. Just saying that, hey, things like PyTorch and TensorFlow, they are not specific to just optimizing neural networks. Okay, any continuous function, as long as you can define appropriate loss function and not just loss function, any appropriate function, continuous function with some parameters, you can always optimize it using PyTorch. Okay. So that actually, that's a great hammer to know, because anytime you have any continuous optimization, maybe not machine learning, mostly in decision making, sometimes you need to do what is called optimization, and when your function is continuous, like for example in the loss function, then you can just do the same things that we did, like do a loss forward pass, do a backward pass and get the gradients, and then do a step. Okay, so uh, so second question was just an example of that. Anyway, I think I went too much into that detail over there. Any questions at this point? If they're minor or specific, then let's take it after the class about that assignment. Okay. So now what I want to do is quickly see where we are in terms of yeah. So we are here, right? As I said, we have to, this project stuff, which is a little bit non-standard next week, but then of course we come back to lectures. So right now, for today, the objective is to finish up word embeddings. Okay, so let me actually look at this list. It's a short list, but so we were here. Okay, we were in module number 4. We were talking about, we saw some other techniques on NLP last time. For example, latent digital allocation, Naive-based, and even CNN-based sentence classification or sentiment analysis work. We just started discussing about word embeddings, and today we'll just wrap it off with a specific detail example of Word2Vec and why it makes sense. How do we get embeddings? And then we'll move on to uh, what are called recurrent neural networks. So recall when I started this NLP topic, I said there are two things that we have to do. Once you have sentences, right? There are two things. First of all, sentences is composed of words. We don't have a representation or a numeric representation, to be specific, of the words, and that was the point of embeddings last time. But let's say we even get so let's say we have access to these numeric representations of words. Still, there's another aspect which is missing, which is how do you handle the sequential nature of words? Right? So word 1 follows word 2, follows word 3, and so on. There's that temporal, or I wouldn't say time, but in some sort of, there's an order relationship between the words. Okay. So how do you deal with the sequential information? And that's exactly where then some new class of models that we'll see come in. In particular, we'll look at recurrent neural networks this time, and hopefully next time we'll look at some additional architectures called transforms. Okay, so that's the lay of the land. So today we'll hopefully get to this and spend time on this. Of course, at the first part, initial part, we'll come back to again revisiting this numeric representation of words. Okay, and yeah, and in particular, they are static representation of words, and I'll tell you what static means later. Okay, so is the lay of the land clear? So yeah, and just to see the lecture goals, let me quickly open that as well before I start the annotation. Yeah. So the objective is, we saw up to this point, right? I mean, we saw that CNN can also be used for an NLP task, in particular the sentence classification task. And what we wanted to do last time, and we did start a little bit with how do we get a decent word embedding using a prediction approach, where we had a throwaway classification task, and we would learn the word embeddings simultaneously while working on this throwaway or an auxiliary classification task. But today we'll look at a specific instance, which is Word2Vec. And later on, the next set of goals are to know are these 4, which are listed here. First one is to know when prediction tasks have sequential can know that prediction tasks can have sequential dependencies, and some of you must have seen time series data. Some of you probably are also working on time series type of data for your project. So that's exactly a good example here. And then we'll see a neural network based solution for dealing with this sequential structure or temporal structure, for example. And that's the recurrent neural network architecture. There's something called unfolding. So you'll see that this neural network architecture is just a architecture which has some repeating blocks, just like repeating layers, sorry. And so people do, when they draw a recurrent neural network, they'll show a folded version of it, and we'll disambiguate what that means. And then a specific instance of a little bit more advanced recurrent neural network block is called an LSTM. And hopefully we'll get time to spend most of the time on this in the second half of this session. And if time permits, we'll look at some applications. But anyway, I'm going to allude to applications, not just this session, but also next session. So this aspect will also be covered. Okay, so that's the lay of the land for today. Any questions at this point? If not, I want to quickly also show something. We will not get into the details, but we'll not get into the details of this code base. And let me just share a link here in the chat. So we're going to look at, so this is just a teaser. I didn't want to go to the annotation and again switch back to the browser. So this is a link to a code base which has comments. Okay, comments on a code which was written by Googlers. So people from, folks from Google Research who actually built these numerical representations of words several years ago. I think Word2Vec is from 2012 or 2013. So that code base, so this link is actually, copies that code base and adds comments to those I guess program files here. Okay. So of course some links don't work. For example, I think this link is dead, which is from Google, but we'll actually rely on this particular author's tutorial, some material from his tutorial as well while talking about Word2Vec. But it's a good resource for folks who are really curious on how it was implemented back in the day, about 10 years ago. Actually, it's written in C, which is not something that we are looking at, but you will see a lot of comments that this author has added to that in terms of what's happening, in terms of building this Word2Vec or numerical representations of words. And then these numerical representations we saw last time were made freely available by Google. So one of the, I think last time what I shared last time, one of the links is using, I think, GenSim. And also this link was shared last time towards the end. Let me just show it to you. Yeah, in GenSim, you can get that pre-trained word vectors. Okay, it's very similar to pre-trained RESTnet, but in RESTnet, you can give any arbitrary image and you can still get an embedding of that image, right? In the feature extraction phase, the feature extraction style of doing transfer learning. Here, words are words, right? Whether you use the same word in a different context, most likely the meaning would probably be similar. I mean, sometimes it may not. And so there are pre-trained word vectors, pre-trained word embeddings or word vectors that are available. And for example, from GenSim, you can get, I believe you can get this, or you can also search for just the string on Google, and you'll get or Google or any search engine, you'll get this pre-trained vectors. Okay, and that's it. So this is the outcome of that code base that Googlers had shared, and this person has commented. This author has commented on what's happening in the code base. Anyway, this is a great reference. It's just that even so, we're going to talk about Word2Vec in a little bit detail. But at the end of the day, you have a bunch of vectors for words. What you want to do is again use TSNE, and we have talked about TSNE several times in the previous couple of sessions. You can look at like you have vectors for words. You can always project them down. And in 2 dimensions, just use TSNE or any nonlinear projection operation, and get a feel for like what are the words which are close to each other. And here I don't think, oh, it doesn't work. Okay, actually, let me see. This nope, this image is very unclear. But you'll see that similar words would be in similar regions of this two-dimensional space, which probably is an indication that these vectors, maybe 300-dimensional vectors, happen to be in similar regions of this 300-dimensional space. Okay, so that's what this at least the first part of this script is trying to do, and then they're trying to do other things. But yeah, any questions about these? About at least the high-level ideas behind these two notebooks before I switch to the annotation, the slide deck. Okay, if not, let me share the slides. Okay. Yeah, if there are questions, even if there are, some question that came up later, just ask on the chat and I can pick it up from there. Okay. So last time I just gave you an example of how you could potentially get the word vector, sorry, vector representations for words. And we were talking about an example, I would say an example where I don't want to discuss too much about it because we're going to look at Word2Vec, but it was basically something like, hey, let's create some classification task that's underlined here. And while doing well on the classification task, which is of course minimize some sort of, let's say, cross entropy or whatever last function we are using, while we are doing that, we can improve the vector representations of the words. Okay, we can start with some random vector representations, let's say random 10 numbers for each word, let's say 10-dimensional vector representation for each word, and then we'll improve, change these numbers again and again and again, just like very similar to how we would change the parameters of a prediction model. And after the classification, after we finish the training of the classification task, we'll drop the classifier itself and we'll just focus on the vector representation of words. That's what was happening last time, and we'll spend some more time on this when we talk about Word2Vec. So that's why I don't want to repeat this step, in a lot of detail, because we're going to look at the same steps very specifically of what exactly is the classification task and so on very soon. Okay. But if we could do that, then the natural question arises, hey, what is, like, you got this vectors of, vector representation of words, how are you gonna, make sense out of it, right? You want to do diagnostics on it. So, and that's exactly what I flashed earlier, or the link that folks can click on that I shared. It's basically just doing, whether you get it from Word2Vec, this is, I'm just writing a couple of names here. Word2Vec is one name for a bunch of vectors that, Google did, and Globe is another set of a bunch of vectors that I don't know if maybe Facebook might have done, I'm not sure, or some research lab. So these are vectors, and how do you get a sense out of them is you can project them into 2 dimensions. That's exactly what the TFNA code was doing from the link earlier. So, and here is a very bad slide, which is actually trying to show words in 2-dimensional space. So instead of looking at this slide, let's focus on a couple of regions, instead of looking at the full slide. And these are the regions, okay? So the previous 2 slides, don't worry about it. It's just the TSNE projection into 2 dimensions, and just the points are replaced by the words themselves. And once we have zoomed in quite a bit, you can see that, for example, in some region, for example, there are all these words which seem to be in the same 2-dimensional space. So the hope is that maybe even in the high dimensional space, whatever, for example, in the 300-dimensional space, if in the case of Word2Vec, they may have vectors which are neighbors of each other in the same neighborhood. Similarly, you can see that days of the week here and months are here, and then maybe other things, right? So things which are not related exactly days or months are also there, but maybe they indicate time. So that's a way to at least look at, hey, are my embeddings good or not? Okay. And it's not like you may have to only work with word embedding. So here's a nice example of a very different domain, which is recommendation systems, right? recommendation systems also have basically some sort of sentences. Okay, where are sentences coming from? When users interact with items, they give a temporal signature of which items they interacted with at what level. For example, they might have seen movie 1 and then maybe seen movie 2 and then movie 5 and movie 8. So that forms like some sort of a sentence for each user. And so once you have a bunch of sentences, now you can now you can embed the words. In this case, instead of words, there will be movies. You can embed movies into, you can get the vector representations from movies. And you've already done recommendation systems in your assignment too, where you are not explicitly doing anything, but you are still getting vector representation for movies. But you can do the vector representation for movies using the same ideas as the way you would get word embeddings. Okay, so since you already worked on recommendation systems in the assignment too, it's good to think about this alternate application. Okay. Yeah, and actually for one of these, I think this is, so the next few slides are mostly going to talk about whenever I give examples, it's mostly about Word2Vec. Okay. Some properties of, diagnostics, basically, we're just trying to get a sense of, hey, does it work? Why, what are properties that it's exhibiting, the vector representations, and then also talk about some extra applications that you can do once you have these pre-trained vectors or, and things like that. So first set, in addition to doing TSNE, the second set of things that you can do is, hey, what are nearest neighbors of some of the words? Right? So you have vectors. You can always ask, hey, given the word, what are some words which are very close to this word? For example, looks like the word France has, these are the nearest neighbors. And for the word megabits, these are the nearest neighbors. So it gives you a sense of whether the quality of the um, embeddings is good or not. Same thing you can do with movies as well. Just again, restart, mentioning the other example, you can take some key movies in different genres and then look at, hey, what are the closest movies similar to this movie that we have embedded, because we learned these embeddings using a Word2Vec style thing. You can actually do this even for your assignment too, to get a feel for whether the movies, whether people watching movies together, together, a high count of users watching two movies together has any, has any impact on whether those two movies themselves have some commonality or something. Okay. Um, yeah. So next, let's talk about a little bit of intuition. So what is intuition for, in general, these embeddings? What we desire, or at least what we want to get out of these embeddings, is that words with similar meanings should have similar vectors. Here it's written as a question, but should words with similar meanings have similar vectors? And the answer is, maybe this makes sense. This type of vector embedding makes sense. And just contrast it with one-hot encoding that we were doing, or bag of words representation that we were doing. There's no meaning of the word, right? It's all, distance between words is always like square root 2 or something, if you think of one-hot encoded vectors. So it makes sense. In this example, for example, whether, operates the largest medical school and the biggest medical school, largest and biggest hopefully have similar vectors, okay, because they have similar meanings. But it's not just, but it's not just vectors that have similar meanings that should be close to each other, right? It can also be words which are not related to each other, but they appear in similar contexts. And that's a generality that we were going for, and we motivated this last time. Words which appear in similar contexts should have probably similar vectors. Okay, so not just limited to synonyms or similar meanings. For example, the inside wall is blue or the inside wall is red. Blue and red hopefully have similar vectors. Okay. Yeah, and similarly, maybe in contrast to, let's say, something like ceiling, which may not appear in same context as let's say blue and red appear as much. Okay, so this is what we want. This is what we want, and this is what we were checking for when we're doing diagnostics. So whether similar meanings, words which have similar meanings are in similar embeddings, and words which appear in similar context, which is the larger goal, the more broader context, whether that's holding true or not. And and the second point, before we talk a little bit more about again, the embeddings a little bit more, is that how much data do we need to get these types of representations of words? Okay. And first of all, we need to see all the words. To get a vector representation of a word, we need to see the word somewhere, right? I mean, in the sense, we need to see the word in the training data somewhere, right? If we don't see the word in the training data, or when we try to learn the embeddings, then out of the blue you give me a new word. It's not like I know the embedding for that, right? It's not like the word embedding function would know what the vector for the word is. But the interesting thing is we don't need to see all the combinations of words. So it's not like we need to see, hey, word one and word two. It's not like they have to co-appear, co-occur together for me to learn embeddings of word one and word two and claim that, hey, they should be close to each other or may not be close to each other or whatever. Okay, we just need to have, let's say, two words. If they're similar, they just need to appear in similar contexts. Okay, it's not so like maybe word one appears in 5 sentences, word two appears in 5 completely different sentences. It's just that now word one and word two could be synonyms. It's just that what we want is wherever word one appeared and wherever word two appeared, there's some commonality in the other words which surround this word one and word two, respectively. Okay? As long as there's some commonality, which is that context around these two words, then these two words will be mapped to hopefully similar vectors. Okay? And this is similar to how we also work. It's not like we look at all permutations or all combinations of pairs of words or triplets of words and so on to get a sense of which words should be next to other words, right? We actually generalize. Okay, we actually generalize, and similarly, and the model itself also picks up that signal that things appearing in different contexts, they should have similar vectors. And so I'm just going over a few more points about the embeddings, and then I'm going to talk about some applications of embeddings, and then we'll talk about Word2Vec. Any questions? You can interrupt me anytime. So this is again, so in between there was a slide about, hey, what are we trying to get to? And that was these embeddings should have some nice structure, that they should be close to each other if they appear in similar contexts. Now here's again something that's true for Word2Vec, or in this case, is the following side effect, which is that if you have vector representations for words, then you can actually do somewhat of an approximate vector arithmetic. So you can actually subtract, let's say, the vector representation for woman minus the vector representation for man. So the two vectors subtract, you will get another vector, right? So that vector could be in some some direction. It's a vector in a vector space, so it'll be basically like an arrow in some direction. And when you compare that with an arrow that you can get when you subtract the vector for aunt minus the vector for uncle, you'll get another arrow. It turns out that those two arrows could be pointing in the same direction, could have the same magnitude, and that's what the symbol is trying to say, that they have similar directions and similar magnitude. So these are the, for example, this vector is similar to this vector, is similar to this vector, and these are supposed to be difference vectors. Okay, so you can think of, for example, a vector space, right? So this is the vector, this is the vector, and so the difference between queen and king is that this vector which is directing over there. And so you would see similarities between things like this. This is just a side effect. If you can get good embeddings, then maybe something like this is true. It's not necessary that something like this has to be true, and if you want this to be true, you can impose that as an explicit constraint or explicit part of your loss function and ensure that the vectors are like that. But this just happens to be a side effect for one of the word embeddings. And the same idea, a little bit more, I guess, stretched out now. Like if you do, vector for France minus the vector for Paris and add the vector for Rome, then you'll get a vector which is very close in terms of magnitude as well as the direction to the vector for Italy. Okay, so this is something that folks have observed, and you can look at this paper. Although these are, I would say, without really looking at the research in too much detail, it seems like a little bit of cherry picking. There's so many words, out of which why did we add these, and then look at comparisons to which ones work and which one doesn't work. But these are all post-hoc things that you could do to get a sense of whether your embeddings are good or not. Okay. Yeah. So these are what I said as some side effects that come about. next few slides, what I'm going to spend time is see how am I going to use these embeddings. And one idea that you've already seen from your assignment 2, first question as well as the when we were talking about images, is literally transfer learning. And here we'll see something equivalent to that, but a few more ideas. Any questions before I talk about these applications, about what I showed earlier? Okay, let me ask question in chat as usual. So now for the next few slides, I'm just going to try to motivate a few, I would say, applications or variants of this embedding idea. Okay, variants of this embedding idea where you may have to even relearn embeddings, but in a more application-specific context. Okay, so if you train, so if you could get word embeddings by this auxiliary classification task, then you can actually directly use them wherever you are using one-hot encoding vectors, one-hot encoded word vectors. So wherever you wanted to, so let's say you were doing some classification and you had extra textual metadata for which you did not, you are not using it because you're not sure how to use it. Maybe you use some other types of features that you created from this text, for example, TF-IDF, or bag of words representation or anything like that. Instead of that, or in addition to that, you can always reuse the embeddings that was trained from before. And that's exactly what you can do with Word2Vec. So you can literally download Word2Vec. It'll have pretty much a word vector representation for many of the words in English. And you can just pick them up and add as extra features, features or feature vectors, concatenate that to an existing feature vector, and once you do this drop-in, I guess not replacement, drop-in addition, you can already maybe see some improvement in your classification task or whatever task you're doing, if as long as that words have some impact on your prediction task. Okay, and we've already seen image embeddings, that's feature extraction, fixed feature extraction, right? We had a pre-trained CNN model weights. Those are fixed, but every time a new image came, we can create a new vector. Here it's not like that. Here we already have vectors for words, and so there's no need for a CNN model or ResNet 18 model, anything like that. Yeah, and this is one way to do transfer learning here, which is literally once this thing is learned, you can use it in any NLP task, which any NLP task will of course deal with words. So wherever you're trying to do anything with words, like for example, your next word prediction, or named entity recognition, or many of the tasks that we've seen. Right, last time there was a URL that I shared called nlpprogress.org. So there are so many tasks there. Any of the tasks you can always use embeddings. Okay. And that is summarized in this picture. Let me just change this to see here. So basically what you do is you learn W and C, which is like, let's say the parameters, the trainable, like W would be like the bunch of word vectors, and C would be some parameters of the classification task. So you learn first this part, and then you can use W in another part, okay, later on. Another part in the sense that you can use the same W once you've trained with C in conjunction with C, you learn the word embeddings. You can use those embeddings for any, using any other task that you want to use. Okay. But there are some more things that you can do. Yeah. So there's some more things you can do, and this is where I said we're going to look at some application-specific things. So so far we've discussed getting representations for words, which means that let's pick a vector space, let's say 300-dimensional vector space, for example. Every word needs to have a 300-dimensional vector. Okay, so we're putting words into some vector space. So what we can do, this is and we'll see in the next couple of slides, is that in addition to putting words into this vector space, we can also put words in a different language into the same vector space, or we can also put other objects like images into the same vector space. Okay, and this will, for example, if you put words in a different language in the same vector space, then you can actually do a very simple translation. service, right? So where you get a bunch of words in the original language, you map all of them into this common vector space, look at the neighborhood of each of these words in the sense, vectors similar to this vector, and find those vectors of the second language which are similar to this vector, and pick a most likely word in the second language, and then you literally get a translated sentence. Of course, there is no order relationship that's captured and all that, but that's one thing you can do. For example, so that's this bilingual word embedding, where, for example, you have English words and Mandarin words, and you can embed both of them into the same vector space. I'm going to talk about the image example a little bit later. So to see visually what we want to do is that we want to get embeddings for English words, and we want to get embeddings for Chinese words, but we want to put both of them in the same vector space. Okay. So, and how are we going to do that? We'll define an appropriate loss function here, which is going to be not a prediction task loss function, but the loss function would be that words that we know are translations of each other should have similar vectors. So literally some sort of a regression style objective or loss function, where we're saying, hey, if I know the vector for university, so whatever be the vector for university, we need to figure that out, right? That's the optimization variable. We need to figure out the embedding of university. And the Chinese word for university, we want to ensure that both of them, whatever vectors we pick, the vector should be such that they have, the distance between those two words hopefully is small. Okay, and if we impose them some sort of a squared loss criteria on these vectors, some sort of Euclidean distance being minimal or something like that, then these two will be aligned, of course. So these two hopefully vectors would be similar, but that will also align many other words, in Chinese and many other words in English to also constrain them to be also in appropriate places. So what do I mean by that? Let's look at a figure. So we are adding this constraint, and for example, we can always have the usual loss function, which is the auxiliary task, where we try to predict whether it's a valid sequence of sentence, valid piece of a sentence, or invalid piece of a sentence, right? That was the task that we saw last time. So if we do that, then we should get similar, like even for word pairs where we don't know that they are translations or their meanings similar to each other, those word pairs would also may end up with similar embeddings. Okay. So for example, after training these two matrices or these two functions, words that we did not know were translations could end up close to each other. And that's what folks have worked on. I think there was a link here. Yeah, we can look at this link or some other links. Like, for example, if we did not know that, let's say this word and business are translations, but it may end up that these two will have similar word vectors. Okay. And here's a pictorial diagram here. Maybe only for some words you may know that they are pairs. For example, sorry, not that one. I think so only for some words you know that they are pairs. I think the highlighted ones probably. So, but by ensuring that these words, vectors for these words are close to each other, you can have pairs that you did not know. For example, maybe here they may end up close to each other. And I think that's loaded in this paper. That's one, I guess, a little bit more exotic example of how to get not just embeddings of English, but also Chinese. But you'll see that actually, I think one of the research labs has given word vectors for almost 100+ languages. And so you can always download for any language, including your native language, these embeddings and start doing stuff related to your own language. Okay, and there is a assignment 3 question related to translation that will use some of these ideas. So we can go beyond words from one language, words from other language being in the same vector space, to words from one language, but also some other objects like images to be in the same vector space. Okay, and that's this example here, where you can map the image of some object to be near the object's word vector. So if you have an image of a cat, you can get tons of images of cats. They should all have vector representations, image embeddings, right? But those embeddings should hopefully all be close to each other because they're all pictures of cats, different types of cats maybe, or different shots of these cats. but also the word vector for cat should also be close to each other. You can impose that explicitly. If you know that, if you know that the labels of these images is a cat, then you can impose this. And and here's a way to do it, right? So you have, sorry, you have, yeah. So you have images, you pass it through a, let's say a deep network, or a CNN, and the embeddings of the CNN, the activations that you can get, activation vectors, and the word vectors, you can constrain them in the last function to have, hey, for a known pair of images and word, the vectors should be close to each other. You can explicitly constrain that, right? So that would be part of your training data in addition to anything related to images themselves or words themselves. So here is an example. Um, like for example, here this pluses represent images of automobile. This red dot represents the vector. Sorry, this pluses represent the vectors for the images of automobiles, and the red dot represents the vector for the word auto. Okay, and similarly, the squares or rectangles represent the images of horse, and the green dot represents the vector for the horse word itself. And you can do this, and then maybe for unknown image, maybe you had dogs and a dog word embedded. If you unknown image, let's say cat we know is somewhat similar to dog in terms of image features. Maybe you'll get a cat, something that you has never seen in your training. You can get a vector representation for this object as well, right? So there, and these are again, you can check out the underlying paper to get a feel for how this is done. So is it clear what's happening here? Let me skip
So
the slide. It's
Professor,
basically the same thing as before. Yeah.
is this used for search by image? Like uh, for suppose we are doing some online shopping and we search by
Yeah.
the image.
I mean, you could do that search by image directly without extra word stuff. But yeah, this is even enhancing that. So first step, great question. So first step is once you have all the image embeddings as in the image activation vectors, right? Feature extraction. Let's say you use ResNet 18, did feature extraction. Once you have these once you have these vectors, you can always give a new image, right? And a new image, you get a vector at the test time. And then you can do just a nearest neighbor search of what other images were similar to this image in terms of this embedded space. And then you can return those images, for example, if you want a similar image. Okay.
Okay.
But here, there's one step more, right? It's just saying that, hey, give me a test image for which I'll get an embedding. And for that embedding, it'll be near some other images embeddings as well. So I can, of course, return other images. But I can also return words, which are because words vector representations are also in the same space. I can return words, and I can now use those words to index back at other locations and return a lot more related things.
Okay.
So yeah, let's do that.
Sure.
Yeah.
Can this be used for active learning?
Okay, so active learning is a completely different idea. I would say, I mean, any prediction task, you can make an active learning version of it. Okay. I would say, yeah, generally any prediction task, some sort of classification regression, you can make an active version of it. So whether this itself can be used for active learning, helping you to pick the next example to train or whatever to get a label for, that I think requires some discussion. So let's not get there. Maybe we can talk about this after the class. Okay. But just for other folks who, active learning is a type of machine learning where you don't get batch data, supervised data on which you train, like what you did in assignment 2, for example. In active learning, you're supposed to the algorithm has to ask, hey, give me a label for this image, and that'll hopefully that when it's asking for the label for some image, it's making sure that that image gives it the most information to figure out the classification boundary or basically the classification weights. So it's some sort of an active querying. It's like a human in the loop type of machine learning. So I'll stop there with that. But yeah, I mean, let's address this question after the class, because I think there's a few more steps that need to be detailed if about how to use this in active learning. Okay.
Thank you.
Yeah. So let me keep the slide because it's the same as before. So now we're going to get into the Word2Vec in a little bit more detail. Okay. By which I mean we're going to explicitly see, hey, what is the classification task? What was the and how are these vectors computed? Okay. And you'll see that the Word2Vec is actually so Word2Vec is an instantiation of getting these vector representations for words, and it actually doesn't even involve any deep neural network. In fact, you will see that it's almost like a logistic regression model, but we will see that in a second. Okay, so just some historical context. So this is a method from about 8 years ago now. Um, I would call it, so it's a predictive method, right? Predictive just means that we are using an auxiliary classification task typically, and we'll see that it is in fact a classification task to learn the embeddings. Okay, so unlike a count-based method, would be something where you're not using a prediction method clearly because it's a different name here. The count-based method is something similar to what you did in assignment to second question. So in assignment to second question, you somehow created like SciJ matrix or some sort of counts for pairs of movies and use those counts to get these movie embeddings, V1 to VM, right? So I would say, I mean, we will not discuss count-based methods here, but that's what I mean by count-based methods. So some sort of co-occurrence is what you would get. If you can compute co-occurrence statistics of words, you can, for example, just do SVD to get some sort of embeddings of, for example. Okay, that's what I mean by that. So Word2Vec is a predictive method. Further, it's actually a static embedding. What I mean by static embedding is that, and the reason why I'm introducing this extra word is that in the next session, potentially, we'll see what are called contextual embeddings. Okay. And these were from, let's say, 2018 onwards, or 2017 onwards, actually. These guys are from 2013 to, let's say, I mean, now, but yeah. So this is what we are seeing. Right? So Word2Vec is a static embedding in the sense that, so what does it mean intuitively? Is that static embedding just means, hey, I got a vector for a word, cat, it anymore. It's fixed. Okay. It doesn't matter whether cat appears in an article which is talking about health of cats versus an article which is talking about pet foods. The vector for cat doesn't change. Okay. In contrast, the contextual embeddings are embeddings where there's going to be an active, so there's going to be an extra neural network involved. Okay. So there'll not be, so in contextual embeddings, you don't get vector representations for words explicitly. What you get is a neural network. And every time you want to get an embedding, you'll somehow run that neural network and you'll get an embedding for the word you care about. But that embedding depends on the context, in the sense that if the word cat appears in an article talking about pet food, the embedding for cat would be slightly different from if the word cat appears in an article which is talking about, let's say, cat's health. So there is a way to use context information to dynamically generate slightly different embeddings depending on the context. Okay, and we'll see that later on. And folks who want to guess it, it's basically one example is, for example, using BERT. Okay, we'll talk about. So this is just an acronym for now. We'll talk about what it means next time. Okay, so I'll not go into details for that for this one now. Let's only focus on Word2Vec.
So, Professor, in general, these days, do they use contextual embeddings or static?
I mean, so I would say, I mean, this is a little bit easier, right? So this is, it involves a messy neural network, which you don't have to handle. I mean, somebody will already give you the train weights for that. I would say this is, so by the way, all this is super new, right? It's just past 10 years. I would say this is more mature and is a stand-in replacement. We just saw that wherever you're using one-hot encoded versions of words or bag of words type of representation, immediately you can change it to Word2Vec and immediately get a gain, okay, huge gain in performance, because now the vector representation of words have actually contextual information embedded in them. Contextual embeddings, are more, I would say, still, I wouldn't say still in the research phase, but still, I would say you do need some amount of expertise to work with them. But they work the same way. If you think of them as a black box, in fact, there are companies which will, which have services, predictions, literally an API service where you send a word and they'll give you the vector back. Okay.
Okay.
So in the first case, you just have to send the word and you'll get back a vector. And the second time you send the word, you get the same vector back. But in conditional embeddings, you have to send the context as well. For example, you send the whole sentence and you get the embeddings for every word in that sentence. And next time, let's say if it's the same word in the second sentence, but the sentence, other words are different, then the embedding will be different. Okay. And so there are companies which literally help you do that. If you're using such companies, then it doesn't matter for you, right? I mean, you just get embeddings and move forward. Yeah.
And in the first one, they use the predictive method, right?
No, we're going to talk about how to get these embeddings and how to get these embeddings. We are still, how to get these embeddings of word vectors. We're going to talk about the predictive method, which is predictive, under predictive approach, Word2Vec is one instantiation of that. In contrast to other ways to get embeddings, which are count based. Okay.
Okay.
So you just think of ways to get embeddings as predictive and non-predictive, and we're gonna Word2Vec is a specific instance within the predictive, I guess, bucket.
Oh, okay, got it. Thank you.
Any other question? Okay, so turns out that paper from Google in 2013, they had a couple of variations, a couple of specific, I would say, classification tasks. So remember what, any word embedding, we said, hey, prediction method means let's attach an auxiliary or an irrelevant, basically, classification task. Remember last session we were talking about, hey, whether the sequence of words is a valid sequence or not, right? So that's some classification task that we cooked up. Okay. Here we'll see a specific classification task that was actually used by folks from Google to create the word embeddings, the static embeddings, Word2Vec. And so that specific classification task, there were two versions. One is called skipgram, and the other one is called continuous bag of words variation. Okay, these are two variations of classification task. We'll actually just go through the skipgram version now. Continuous bag of words will be very similar, so it's just I don't want to discuss it in parallel. Let's first look at skipgram first, and if there's time, we'll just comment on continuous bag of words classification task. Okay. So for us, we just need to remember this name. Oh, there's something called skipgram, but we'll actually in the next few slides disambiguate what exactly do we mean by a skipgram classification task, a skipgram model. So what is the skipgram classification task, or how do we learn word embeddings with this type of a classification task? It turns out that the underlying thing is a very simple, I wouldn't even call it a neural network because there's no nonlinearities, but you'll see that the underlying, if you really write down the classification model, definition, it just is some sort of a neural network. It's very similar to logistic regression stuff that we saw several sessions ago, or let's say one hidden layer neural network that we saw several sessions ago, or in assignment 1. Okay. What we'll do essentially is we'll train a single hidden layer neural network, and we should be by now we should be familiar with this because you also did this in assignment 1. Single hidden layer neural network, and we'll do this auxiliary task, and that auxiliary task is just people call it skipgram. Okay. And the auxiliary task is actually just a classification task. And while trying to do well on the classification task, like let's say minimizing cross entropy loss or whatever it is, we will be able to learn the word embeddings. Okay? And so these word embeddings somehow will be related to weights of this neural network, this single hidden layer neural network. Okay? So there are two parts. There's a classification task, but we want word embeddings. Both are somehow represented in just this single hidden layer neural network. Okay, and we'll see the diagram to really drive home the point in the next couple of slides. Let's talk about the classification task first, okay? Because this is just about the data. So what is the classification task? Forget about embeddings for now. What is the task? The task is we'll pick a word somewhere in the sentence. Okay, it doesn't have to be middle, but pick a word, and pick one of the nearby words. Okay, so we'll see an example in the next slide. Pick one of the nearby words, and then our classification or our prediction task is to say, given this word, predict that nearby word. Okay? So that's as simple as that. So you want to say word is the input, and you want to say word is the output. That's what you want from the classifier, and so your training data would be word pairs, right? So hey, for this word, predict that word, and for some other word, predict some other word. But how do you get this training data? You're saying, hey, if you have sentences in, let's say, corpus of data, text data, pick a word and pick a nearby word, and that's your training example. Okay, and that's it. So that's input is a word pair. Sorry, not input, but input is a, let's say, a word, and output is a word. Output is a normalized course, but okay, I'm saying normalized course here, but just think of output as like some sort of a bunch of scores, one for each word. Okay, so one for each word, and the word which is the right word should have the highest score, right? Very similar to classification. If you know the output has to be label number 3 correspond to some particular label, then you want the score to be highest to that label and everything else to be close to 0, right? So that's what I meant by output here. So what is nearby? Nearby is as simple as, hey, let's pick a word and let's talk about a window size, which just means that, hey, let's look at 2 words to the left, 2 words to the right, or maybe 5 words to the left, 5 words to the right. And in this example, I'm just saying 2 words. Window size 2 means 2 words to the left and 2 words to the right. So those would be considered nearby words. Okay, that's just the definition of nearby that we are using here. Okay, so let's actually look at this example a little bit more clearer. So let's say the example, so let's stop the sentence here, but let's say the example sentence that we have, let's say one sentence in our corpus is this sentence, okay? The quick brown fox jumps over the lazy dog, okay? So what we'll do is now create training data, okay? So input, output, and data. So we'll say, hey, let's focus on the word D, okay? What are some nearby words to the word D? Okay, since it's the beginning of the sentence, there's no words to the left, but there are a couple of words to the right. Let's say window size is 2, which means that my training data will be D and quick, D and brown. So, okay, 2 examples I got. Okay, so what does this training data mean? Whenever I input D to the classifier, it should output me. So for the first example, it should say output is quick. For the second example, it should say output is brown. Now you can say, hey, how can, for the same input, I can predict 2 things. I can predict one of the classes quick to have the highest score, or brown to be the highest score. But you can imagine, roughly what we want intuitively is that whenever the word D comes in from the input at the input, at the output, we just want the scores for both quick and brown to be high enough. Okay. Similarly, let's look at the last, this last example here, last version. So let's say the fox is the input to the classifier. We give the input fox to the classifier. Anyway, the fox word will get into some vector representation, and we're going to talk about the vector representation. Once you give fox as an input, eventually it should output, it should have high scores for its nearby words. Okay, so in particular, one example is going to be fox and the nearby word quick. Second example is going to be fox and the nearby word brown. A third example is going to be fox and nearby word jumps. And fourth example is fox and nearby word over. Okay, these are all training examples. Okay. Of course, for the same word, if you want to predict 4 different things, we just want to intuitively that the 4 coordinates of the score vectors, they have hopefully high values. Okay. Is the example clear of what the training data is?
Professor, I'm actually confused.
Mm-hmm.
So do you think it's actually doing the combination of the words which are there in the sentence? Because I see that in the example, or how is it actually happening? I'm confused.
No. What we want is a classifier, right? Let's call it, C. It takes word as input and needs to produce word as an output. Okay. And let's talk about how can a classifier produce a word as an output, right? So just think of the classifier being a, let's say our vocabulary size is 10,000 for simplicity. then the classifier is basically producing a 10,000 dimensional score vector. Okay. So far in ImageNet, for example, we said, hey, number of classes is 1,000. And CIFAR 10, you only had 10 classes. But here, just think of the number of classes is 10,000. Okay. So, and of course, each coordinate will be, there's a corresponding word for it. Okay. And that's how we're getting outputting a word. So if we score for, let's say, the 10th coordinate is the highest, then the word corresponding to the 10th coordinate is the output word. Okay. So is the output clear? Output is just going to be a 10,000 dimensional classifier, right?
Okay.
And the input is just a word. Again, now what is the input that we're going to give? Just a one-hot encoding. Okay, so if the word is D, somewhere it's 1 and everywhere else it's 0.
Okay.
But what I'm saying is this one-hot encoded representation word, eventually when we train this classifier, it will have that W. It will have that, we will learn the word embeddings. Okay.
Okay.
So it turns out, so this thing happens to be a neural network. In fact, one hidden layer neural network. And you'll see that the first layer or the layer which gives you the hidden activations, the weights corresponding to it essentially give us the word embeddings. Okay. So, but yeah, so input is this, output is a word. And that's what the training data is exactly this, right? Input, output, input, output. Now you can say, hey, for the same input, why am I getting two outputs, right?
Yeah.
Yeah. So that just, intuitively what I'm trying to say is that when I do, let's say, when I pick the first example, I want for me the loss to be low. I want quick coordinate to be high and everything else close to 0. For the second example, if I want loss to be low, clearly I don't want quick to be high, but I want the brown coordinate to be high, right? So they both somehow are contracting each other, and you can imagine that it'll ensure that all other words have low scores, but quick and brown will have reasonably high scores. That's all.
So when you get the
Not a
second
contradiction.
output,
Mm-hmm.
okay. So when you get the second, when you get the second output,
Yeah.
so the quick will already have a higher score compared to brown. So why didn't it return quick again?
No, it'll. So remember, every time you pass a word, you'll get a score vector. All I'm saying is, if remember, if your training data, you only had D and quick as the only training data. Let's say your classifier really learned the mapping well, then only quick coordinate will be high and everything else will be 0, right?
Yes. Yes.
Ideally. But so in the alternate case, when you only had D and brown and not D and quick, then only the D and brown coordinate hopefully will be high and everything else will be 0. Now you have both. What I'm saying is, it turns out that both, the parameters of the classifier, whatever W and let's say not theta, but whatever W prime or W2, whatever, they'll be such that only these two scores will be somewhat high, maybe not the highest, and everything else will be close to 0. Okay?
These two you meant the brown
these two
and
coordinates. Yeah. The coordinate
brown
for
and D.
quick and brown. Yeah.
So you're saying that the value for D and quick will be high for the first.
No, D is the input. D is the input.
Yes.
All I'm saying is, given the D as the input, the coordinate quick and the score for a coordinate brown, those will be somewhat higher than everybody else, because we have both those examples in the training data. That's all. So of course, one of the examples wants quick to be highest, the other example wants brown to be the highest. So they'll, of course, somehow, the best way to do it is to have both of them somewhat high scores, and everybody else, anyway, we know everybody else, it's very clear what we need to have scores to be close to 0. Just for quick and brown, we just want a little bit higher scores. That's what's going to happen.
Okay, got it. Thank you.
Yeah. So hopefully the training data is clear. Now we're going to talk about setting up the network, okay, neural network. And again, this is now that you've seen CNNs and much more complicated neural networks, this one will be, you'll see that the underlying neural network is very simple. One hidden layer feed-forward neural network that we've already seen in the second session. So here's this is not exactly Word2Vec in the sense that Word2Vec has much more number of words. But here, for the sake of discussion, let's assume that the vocabulary size is only 10,000, okay? Which means that, let's say, there are only 10,000 words in English. Word2Vec has, in the real embeddings that you can download from the internet, they are many, many more words. I don't really remember how many words there are, but there are more words, okay? So let's say we have 10,000 words. Okay? then the input word, as I said, is just going to be a 10,000 dimensional vector. It's just going to be one hot encoded vector. We just here, right? So this is one hot encoded vector for whatever is the input. Okay, and then yeah, that one hot encoded vector. The true label is also one, 10,000 dimensional vector, right? Although we produce scores here, I want to compare the scores versus one of the, let's say 100 encoded representation. Only quick will have value 1 and everything else will have the value 0, right? For example, for the first training example, right? So 100 encoded input, 100 encoded output. And the network or the classifier has just produced these 10,000 scores such that the coordinate which is the right example in the training has the highest right output in the training has the highest score, right? That's same intuition that you've been seeing about classifiers quite a bit. Yeah. Any questions up to this point before I now flash the before next talk about the explicit like a diagram for the neural network? Yeah, I mean, yeah, go ahead.
I have a question. So the word that, or the corresponding word that has the higher probability, so it will be near the input word, yeah?
Yeah, I mean, we want that. Yeah, exactly. We want a classifier which, yeah, we want words which are near the input word to have higher probabilities. Yes, and that's why we are creating training data like that, right? So, for example, in this last one, Fox nearby words are these 4 words. Okay, so we just want those 4 word scores to be highest whenever I give Fox as an input.
Yeah. Okay.
Yeah.
Okay. Thank you.
Yeah. And just to be clear, it's not that will only be with these 4 words, right? So remember, if let's say there's some other sentence, okay, where Fox also appears, there'll be some other words nearby it, and those words also we want scores to be highest. So it's not just, for one sentence we got so many training examples. For other sentences where the same words occur, there could be many more, examples. Okay? Just so that it's not just these many examples. It's not that the words only appear in one sentence. And that's where the strength of the method is, that if Fox appears in a word, in a sentence like this, Fox jumps, okay? And maybe in some other location, the word Fox appears with, say, Fox walks, then jumps and walks would probably have similar vectors, okay? We want jumps and walks, for example, to have similar vectors, for example. Or for example, cat jumps, maybe cat and fox can have similar vectors because they appear in similar contexts. Anyway, let's look at the network first. So the network is as follows. So as I said, input is a one hot encoded vector. We have 2 layers, one hidden layer. And okay, the hidden neurons are just represented using these orange circles here. The sigma just represents summation. Okay, so don't worry about the notation here. It's just summation of, remember every neuron, it has its own weights corresponding to it. And so weights times the input is what the neuron, produces a single number as output, right? In a we saw several times. So there's a bunch of weights here, and there's going to be a bunch of weights here, right? I don't want to use, let's see. I don't want to use a notation here. Maybe there's some notation in the next slide. I don't want to use that explicit. I don't want to guess the notation right now. And then what we're producing is scores, right? So we're producing scores. Okay. And in fact, the scores are already transformed into probabilities. Okay, and we know exactly how to do that. Scores, once we get scores, we just apply a softmax operation and we get probability, right? It's just e to the power score divided by e to the power score for everybody in the situation, and that you get a normalized number, and that's probability. And that's what is represented by this circle here. It's already like after you do the softmax operation, you get this you get the probabilities here. And that's it. That's the neural network. So it's basically just two pairs of weights. Let's ignore biases for now. I mean, if you recall from your one hidden layer stuff, then there were also biases in addition to the weight matrix. So let's not worry about that in this architecture. Okay, so now the objective is, as usual, when we did classification, we know we had cross entropy loss as the objective, right? We wanted to minimize. So here, it's somewhat very similar. Okay, it's going to be the following objective. So let's say training data has capital T words, okay, and has a window size of 2, which means that every word, roughly, there's going to be 2 words before it and 2 words after it, which you want, which is going to be part of the training data. So each word will give us basically about roughly 40 number of training examples, right? Each word will have like 2 guys in the left side, 2 guys in the right side. So those are all my training examples, okay? Roughly, it's all rough calculation. So for each of these 40 number of training examples, I'm going to have an objective which I want to maximize, okay? Instead of minimizing loss, now I want to maximize something. So what am I trying to maximize? I'm trying to maximize so this summation is just saying sum over each word, sum over each word, okay, sum over all the neighborhoods, okay, neighboring words for each of these words. What I want to maximize is the log probability, okay. So log probability of this neighborhood word given the word, okay. So so this is maximizing this log probability is the same as minimizing the negative log probability, okay. And that's if you want to think about losses, we're just talking about minimizing the negative of this, okay. Now what is this trying to do? So let's think of a word tray, right? So in the previous example there was fox and jumps. So given the word fox, I want to maximize the log probability of the word jump given the word fox. That's all. And where am I getting this log probability is exactly what the neural network is producing, right? Given the word fox, it's producing a bunch of probabilities, out of which I look at the probability for the word jumps, and I want that probability to be highest. Set the parameters of the network such that the probability of jumps is highest given the word fox. Okay. So I just, this summation is just doing it for every word, every neighborhood, each one of the 4 neighborhood words that every word can potentially have, just maximize the log probability of the nearby word. And this is where the neural network is. The neural network is right here. Any question? I mean, neural network's input is this, output is, output is going to be a score for every word, but we care about the nearby word. What is that score? And that's the log of that score, log of the, I guess, the normalized score, and therefore the log of the probability is what we want to push up. And how are we going to maximize this? Again, we'll just do gradient descent anyway. But so we'll not worry about optimization. Yeah. Okay. So next, what I want to do is now I want to interpret. We have this neural network. We can do this maximization, and we'll get a bunch of weights, right? A bunch of weights, as in like this guy and this guy will get. We just want to, what we're going to spend in the next couple of minutes is just to interpret that the first bunch of weights can just be called word embeddings. Okay, and that's exactly what Word2Vec paper from 8 years ago does. Okay, with some extra bells and whistles for dealing with large scale of data and all that. So we'll kind of ignore scale of data here in this intuitive illustration of Word2Vec. But that's what we're want to do. We're just going to try to interpret the first set of weights to be the word embeddings. Okay, so yeah, let's call the first set of weights to be actually W0 instead of W. And why is that? Is because I want to consider its transpose to be W. Okay, so what is happening in the first set of S? Remember, so WX plus B, let's forget about the bias. Okay, there is plus B, but just think of plus bias to be all zeros, and we're not optimizing it. So WX is the hidden. And also one more point I forgot to mention here is there is no nonlinearity, okay, in the hidden layers, in the hidden neuron. So think of the neuron doing that inner product, and then there is no ReLU or there's no sigmoid, anything like that. So just think of the identity function there. Okay, so no nonlinearity. Now, so this is what is the hidden vector. Hidden vector is just going to be W times X, right? Plus B, but B I said is let's say it's 0. Now, what I'm trying to say is that let's call the first step as 0. So first transformation, first linear transformation, as something like W0 times X. Okay, so let's call the first weight matrix W0. Why is that? Because I want to transpose it. So somehow like H transpose is equal to X transpose W0 transpose, I want to call this to be W. Okay, just and what is this? I remember X is supposed to be 10,000 cross 1 dimensional one hot encoded vector, right? X is just the one hot encoded vector of which word it is that I want to input. Now, therefore, W0, the number of rows of W0 is going to be 300. Okay, so why is it 300? I think again, did not emphasize it here. I said the number of neurons in the hidden layer, we're just going to choose it to be 300. Okay, and that's just the architecture that they chose. So we are just going to follow that. And, so we know that W naught, the number of rows should be equal to 300. And if I do a transpose of it, now 300 rows and 10,000 columns, if I transpose it, I'll get something like 10,000 rows and 300 columns, right? Now, and the reason I want to transpose it is because each row, I'm going to think of it as a word vector of this weight matrix. So that's the only reason why I am introducing extra intermediate notation called W0. But at the end of the day, what I'm trying to say is that the weight matrix of this one hidden layer neural network, the first one, the one was the input, the one which multiplies the one hot encoding vector, is essentially the word embedding matrix. Okay, and so each, like if you think of W as this, each row, there are 10,000 rows. So each row, which is 300 dimensional vector, is essentially going to be considered the word vector. Is essentially going to consider the embedding of the word. Okay. That's our definition. And any questions up to this point?
What was the number of columns? It represents which parameter? Can you just repeat this one?
Oh, number of columns is going to be the number of, so in terms of W here, there's going to be 300. Okay.
Yeah.
Neural network, in the neural network, it's going to be the number of neurons. Okay. This 300 is just because if you think of the transpose, right, number of rows, hidden vector, if it's 300 dimensional, then the number of neurons is 300 dimensional because each neuron is going to produce one number, right?
Okay, so we will set this parameter. For example, now you just
we chose this to be 300.
Yeah. Okay. Yeah. Thank you.
Yeah.
Okay.
Number of hidden units you can choose anytime, right? So you choose a 300 or whatever, 10,000 or 30. It's up to you. Yeah. The Google folks, they chose it to be 300 in one instantiation. Yeah.
Okay. Thank you.
The ones that you can download, from the internet. If you want you want the static embeddings, they will be 300 dimensional.
Okay, thank you.
Yeah, they might have trained bigger ones. I'm not sure. Yeah. Okay, that's it. I mean, that's exactly the notation here. So what I'm saying is that if you transpose it, then you have 300 neurons and you have 10,000 rows because there are 10,000 words, and you can just look at each row to be one word vector. Okay, and this is our real goal. Our real goal is to just learn this first set of weights. Okay? Once we learn the first set of weights, we're just calling them to be word vectors in this neural network and in this particular classification task. Okay? As long as we can do well in the classification task, whatever classification task by just maximizing this objective, whatever weights we get, we're just going to interpret the first set of weights to be word vectors. Okay, that's what is happening in Word2Vec.
So these are the word vectors that we can use it for any model, any.
Yes.
Oh,
Yes.
okay.
So think of that one hidden layer neural network. There are two sets of weights, right? One going up to the hidden layer and then from hidden layer to output.
Yeah.
Output score. Let's not worry about the weights going from hidden layer to output. We're gonna forget it. Okay? That's like the auxiliary classification task related thing. Yeah, the weights which are going from input to hidden layer, those are what we call gonna continue to reuse every time, and that's exactly what you can download from the internet, like via Jensen that we saw earlier.
Okay. And if the here it looks like we have 10,000 words. My example might have maybe 100 words. So it will select the word vectors that we want to use, or it is going to use all the word vectors and see which matches the words.
No. So the example that you gave, is it once you already have trained word vectors how do I use it for my sentence when my sentence has 110 words or something?
Yeah.
What's the question?
Yeah.
Yeah. So every word there's a corresponding vector, right? So if you have a sentence with 10 words, the vectors correspond to those 10 words.
Okay. So
Right?
okay. So my model is not going to take all the word vectors. It is going to see the vectors which is useful, and it will take it and it will return.
No. Whatever the classification task we do, at the end of the day, we get a bunch of weights, right? The first set of weights, second set of weights.
That's right.
Now forget about the whole classification task. Just take the weights of the hidden layer, like from input to hidden layer. Okay? That's this matrix, right?
Yes.
That's it. I mean, that's some bunch of numbers. Now I'm saying anytime you have a word, if you just want a vector for that word, you just look up that row for that word, and that's your vector for that word.
Okay.
For any other task. Okay. You forget about this original classification task and all that stuff.
I wanted to know that, okay, how do we
in the
so
training, how do we do it? Yeah, we're gonna maybe we'll
the looking up thing that
oh, it's a lookup. It's a lookup, right? So just think of a dictionary or some, it's actually not even a dictionary, right? If you have a matrix, you can always index a row, right?
That's
in Python, NumPy array, you know how to do it.
Yeah, that's right. Got it. Thank you.
In fact, and there's actually a nice interpretation here is that when we multiply this one hard encoded vector, let's say we're talking about the word cat, okay, it'll have some coordinate, to be 1 and everything else to be 0, right? In the one hot encoded representation of the cat. I mean, it will correspond to some index in that 10,000 rows. Okay? But when we multiply that one hot encoded vector cat with this matrix W, okay, we are actually going to get that row. Okay, so just this X transpose W. W is what? 10,000 cross 300, right? Now X transpose this 100 encoded is 1 cross 10,000. Right? I just took a transpose. So the output is going to be 300 dimensional vector. Right? You can see that the dimensions match. Right?
Yeah.
This is 10,000. This is 10,000. So if you hit the embedding matrix with the 100 encoded vector, you literally get that row corresponding to the cat.
Okay. Got it. Yeah. Now
And this is exactly what's happening. Yeah, this is exactly what's happening even in the neural network. So whenever I was giving one hot encoded as an input for any word, I was just picking a row out of this embedding matrix from one point of view. Okay. And that row was that hidden vector. Okay, the 300 dimensional row was the hidden vector because the number of neurons is 300. So I got the 300 dimensional vector.
Okay.
There I'm just trying to say, hey, given this embedding, can I predict the nearby word score to be highest? Okay, that's the classification task.
Got it.
Like
thank you, Professor. This
jumps.
actually was easier for understanding. Thank you.
Okay. Anybody else has any questions? Yeah. So I was just saying, what I was saying is that if you have what's it called? A 100 encoded vector, and the index of that wherever it's 1 just corresponds to picking up that row of that matrix. Okay. So in this example, there are 5 rows, and if the fourth index of the 100 encoded vector is 1, then you just pick the fourth row. That's exactly what's happening in the input of getting up to hidden vector values. Okay, just repeat of what we just discussed. And yeah, once you get that 300 dimensional vector for your original 100 encoded word, from there you're saying, hey, how do I get from this 300 dimensional vector to ensure that after multiplying this with another weight matrix, we don't have to even name it, and then doing a softmax operation, I just want the nearby words location. So this is going to be 10,000 dimensional vector. I just want the whichever is the nearby words, those scores to be highest. Okay, by the way, x-axis just means higher score, or low score here, and everything else to be close to 0. Ideally 0. Yeah, that's all we want to do. Yeah, and this part is that once you have a 300 dimensional vector, how do we get to high scores here? So we're learning both these weights and these weights. Okay. Before we get 300 dimensional. We are learning the 2 sets of weights in the one hidden layer neural network, right? It's just that the first set of weights, we're just interpreting them as word vectors. And let me just see. Yeah. So, and this is probably a key slide, although it's just trying to explain why again, just say it's a repetition, but again, why would we get words which have similar context to get similar, similar context to have similar vectors, vector representation. We just understood the architecture, and we understood, hey, we can interpret the first input to hidden as like just word vectors. But why would the word vectors end up happening to have similar vectors if they have if they happen to be in similar contexts? Okay, so we're going to reason that. Okay, so two words, two different words have similar context, which means similar neighboring words, right? Which means the words that are likely to appear around them, they are similar to each other. Similar context just means words that are likely to appear around them are same. Then what we want is that the output probability vector should be similar, right? So let's say the fox has jumps, and cat also has jumps as a neighborhood word, which means that whether I pass fox, whether I pass cat, the score, the score vector should be such that the jumps coordinate should have some, decent score, right? Right. So if the output, if the jumps coordinate has to have high score for both when I pass fox or cat, and since it's only a linear transformation, once I have this, once I have this vectors, it's only a linear transformation, right? Remember, from H I can do another transformation. Let me just call it theta to get the scores, right? So I want the score for jumps to be highest, which means whether I pass fox or cat, it should be the same score coordinate should be high, which means that H should also be similar. Okay, because it's just linear transformation, right? It's not like linear transformation is gonna non-linearly change two vectors, right? It's gonna scale and transform and rotate whatever similar vectors in similar ways, right? So if you want high scores at the similar context coordinates, then it better be that the original words have similar word vectors. Okay. Yeah, for output, essentially, I mean, here's the punchline. I mean, and we can talk about it maybe even after the session is over, is that if the output vector has to be similar, which means that, hey, both fox and cat have similar nearby words, and therefore similar, they should get high scores in the similar words, then hopefully fox and cat have similar word vectors themselves. Okay, because the output vector, whatever the score vector or the probability vector, if they have to be similar, then the word vector has to be similar because there's only a simple linear transformation going on, right? So that's the key idea here. Yeah. The original input, since the original inputs are one Hamming distance apart, in the sense that the original inputs, the one hard encoded distance between fox and cat is always, square root 2 if you think of Euclidean distance or whatever, some two different locations, right? So yeah, since the original input are always fixed, the only thing that can be brought close to each other is that these word vectors, and they have to be brought close because the outputs has to be similar, and there's only a linear transformation happening in the second part, right? From the hidden layer to the output, there's only one linear transformation happening up to get the scores. Of course, there's a nonlinearity to get to softmax and get the probabilities, but modulo that. Okay. Yeah, what I'll do is not again repeat the point because there's a chance of confusing you guys. So I wanna not show anything first and ask if there are questions.
I had a quick question, and
Yeah.
you might have said this and I just missed it, but
Yeah.
obviously words don't appear in the same rate. Words like the or he or she appear way more often than even something common like cat.
Yeah.
So when training the model, is it normal to do some normalization on that, like change the input data so that is more regular? And do you then, once you have the weights, do you do normalization on those weights, or is that typical?
Normalization as in divide all the weights by some
you try
their
and make
magnitude
it
or something.
Yeah, try and make the weight or the vectors similar lengths or something like that.
No, for the second part, it's for the whether normalization or not. No, we don't do any normalization, at least.
Okay.
Yeah. But the first part is exactly here, which I did not want to get into. But I mean, in the sense that there are some engineering tricks that you need to do. I would say when I say engineering tricks, it's just extra implementation details, okay, to get the core idea working. Because when you work at the level of working with billions of sentences and maybe hundreds of thousands of words, Okay, because it's not exactly the words of the proper English dictionary, but they also include many other things. Yeah, you do some things. Like, for example, to deal with this fact that D appears so many times and articles appear so many times, you do delete, actually. You delete them proportion. So the way these guys do it is they delete them proportion to how frequent they are. So the first time they keep counters of how many times they saw a word, and every time, and the next time they see that word, with some, they flip a coin, which the coin's bias is dependent on how many times you saw the same word before, and you drop it.
Yeah.
Yeah.
I imagine there's a ton of ways to
Yeah.
approach, simplifying
Yes,
your
yes.
data set,
Yes,
and it's a
yes.
bunch of design decisions. I was just curious,
Yes,
if they did anything at
exactly.
all. Okay, thanks.
Exactly. So you don't have to do it. So this seems like a somewhat weird way, but yeah, there's different ways to deal with this imbalance. Yeah. Yeah. Good point. And they also deal with something else, which is called negative sampling. I strongly encourage folks to look at it if you have time. It's about the fact that, let's say in our example, right? So 10,000 words times 300 dimensional vectors for each word. This already, how many are there? 300, and then 1, 2, 3, 4, right? 4 zeros. How many is this? So 3 million. Sorry, 3 million numbers, right? For one set of weights, from going from one hot encoded to hidden, there are 3 million numbers. Similarly, from um, hidden to output, there's another bunch of 3 million. So there are 6 million numbers to be touched or updated, right? That's a lot of parameters. And this is being done, and you can imagine the actual version will have so many more words, right? So the number of parameters to update is too many. Okay, so there's one more trick that they actually employ in the paper while coming up with these word vectors, is that they'll say, hey, although I'm producing scores for every word, okay, what I'll do is I'll only update the weights for weights, forget about neurons, but only update the weights for a few non-nearby words. Okay, so which just means that when I produce, I need to do backprop, right? So I need to predict the right word, nearby word. And of course, I also predict zero, hopefully zero score, and therefore zero probability for the non-nearby words. Okay, and there's going to be many non-nearby words, right? So there's going to be almost 9,999 non-nearby words, for example. You can't now backprop all the words and update all the weights in every gradient descent step. What you'll do is, for the nearby word, and the weights that were related to it, you're gonna update them. Hopefully change the weights appropriately. Similarly, what you'll do is some non-nearby words you'll pick, maybe 5 or 10, and then only backprop on them. Okay, that way these scores are off, they should be close to zero, or these probabilities are off, this probably should be close to zero, something like that. Okay, that's what they call the negative sampling. I would say it's just a trick to deal with this huge number of parameters. So I think for us, for the first iteration, we don't have to worry about it. But folks are interested in doing something like Word2Vec. Maybe you have this recommendation problem, right? Very similar to what we did in assignment 2, question 2. So if you have, let's say, 1,000 movies, and you're only getting 1,000 movies and 1,000 users, it's not that big of a forget about users. If you have 1,000 movies, and if you're only getting 5-dimensional vector movie embedding, then it's not too much of a big deal. But if you have 1,000,000 movies, and each movie embedding is supposed to be 300 dimensional, now you have a challenge, right? To deal with how do I do gradient descent and all that. So these tricks come into may help in that situation. Okay? So in real practical applications. Anyway, so I didn't want to comment too much on this. Yeah. Yeah, so vocab size in the reality was about 3 million. So it's quite a bit. And they actually not just look at, they look at even compound words are basically pairs, n-grams also. Okay, so for example, you can see things like this with an underscore. So that's why they have a huge vocabulary. And so they had to deal with how do we deal with such a huge vocabulary? Because 3 million times 300 dimensional vector is a huge number, right? So yeah. And as I said, GenSim has ability to load. Okay, so I think you have to download the vectors themselves, I believe. And once you have the downloaded vectors and it's few gigs in size, then you can just get similar vectors to a keyword and things like that. Okay. And you can go back to that TSNE example that's listed in the chat to also see how to do this. Yeah, I think what I'll do is, because we are, I'll skip this other variation of the classification task. Once we understand one variation, it's good enough. The second variation is a twist on the same type of idea, so we'll skip that classification. Yeah, and we have already seen an example code. In fact, that was in C. If you want to see other example codes, if this link doesn't work, just search for TensorFlow Word2Vec and you'll get an example tutorial on implementing Word2Vec. And as I said, there are also other embeddings available. I think Glow is the other one. It is an acronym for something, but I don't remember. So that's another popular one which came around the same time. But there are many others, static embeddings. Okay. So let me actually check if there are any questions at this point, because we want to switch topic to that. Now we have some idea of getting embeddings or numeric representations of the symbols, words. Next, we will talk about how to capture sequential information using neural networks. We already know how to capture sequential information in time series data using some conventional methods like vector autoregression or ARIMA. If you haven't heard of these names, don't worry. In a conventional time series class, you would see some of these methods, but we'll see how to use neural networks to deal with temporal structure. And sentences do have temporal structure, but in general, also there's going to be temporal structure we want to exploit. Any questions at this point? Okay, let's take a break then. Let's break till 8 p.m. and resume at 8. And I will switch over to RNNs and we'll discuss that. And if you have questions, yeah, put it in the chat or I'll stay back. Of course, we have office hours right after, so we can discuss more. Okay, so welcome back, everyone. So I wanted to, before I switch over to recurrent neural networks, I wanted to show you a quick tangential thing, which is an example of what can be done, what interesting artistic things can be done with image processing. So here, this is about reproducing images with geometric primitives. So this is a nice, example code base that you can look at. Basically, what it does is, given an input real image, it tries to approximate the aspects of the image using geometric objects. So you can see that going in here. For example, to get this image, it's using ellipses of different shapes to get the pattern. So get the person's, get this person's pattern. So just wanted to share with you as an example of how it's, to figure out which pattern, which sized primitive object to put where. There's of course some optimization going on, and so it's worth looking into how this is happening. Anyway, for folks who want to get more inspired in terms of what project to work on, is a good example. And this was the link that I was showing. Okay, so let me again share my slide deck. Okay. Yeah. So what we're going to do now is now talk about this temporal structure, as I was mentioning right before the break. So we'll start with what I would call vanilla recurrent neural network. So there is a way to, uh, so this first set of topics, or first set of topic, first topic in the set is we're going to just discuss what is a recurrent neural network and how is it wired together, what are its parameters, and so on. And then we'll look at a specific popular instance of a recurrent neural network, which has a slightly different wiring. Wiring, I just mean slightly different subcomponents. All of these are neural networks, but slightly different subcomponents and slightly different building block. It's called an LSTM, and we'll look at that potentially later this, if you have time, or maybe early next class. Okay? And along the way, we're going to talk about, in general, what types of problems can be solved using recurrent neural networks. And hopefully next time we're going to talk about, which is not listed here, is called attention. Okay? It's a word which means many different things for many different folk, but attention in deep learning, there's a couple of instantiations of something called attention in deep learning. One of them we'll look at when we talk about LSTMs, or in general, we talk about RNNs. And in the next class, hopefully we'll talk about transformers. And this is something that I alluded to earlier, some acronym called PERT. Okay, we'll talk about what these acronyms mean. I mean, this will this certainly we just said it's recurrent neural network. This one is just means long short-term memory. We'll look at it next time. And the topics that we'll look at is basically in the next session, we're going to focus a little bit on attention. And then, of course, we'll also look at a slightly enhanced or a variation of attention in a popular class of models called transformers. Okay, so I'm just telling you the overall context so that we are here, but we'll talk about LSTMs. Then we'll talk about, of course, we'll talk about applications, throughout the discussion. And then we'll talk about attention using LSTMs or RNNs first. And then we'll talk about a new class of models, and they'll have their own set of, how do you do attention. Okay, and I'm not going to define anything about attention right now because that it requires explanation and examples. But just for your information, there's going to be something called attention later on. Okay, so let's start with RNNs. Here are the application categories, types of problems that we can solve. Okay, so far we've only scratched the surface in the sense that we only solved one type of a problem, okay, which is basically one-to-one. Okay? Which is, for example, you have a fixed size input vector and you produce a fixed sized output vector, a bunch of, let's say 10-dimensional scores given a fixed sized input. If not, it doesn't have to be a vector. For example, the CIFAR10 that you worked with, is a fixed size tensor. Fixed size tensor, fixed sized tensor as the output. You can, but there's so many other variations that you can do, and many of these variations involve sequential information. Okay, I mean, sometimes you don't need to have sequential information, but there you don't care about what follows the other. For example, think of it this way, right? So if you have a sentence, if you have word embeddings for each sentence, right? Then you can say, hey, once you have word embeddings or word vectors, you can say, hey, one vector follows the other. Okay, you can have an order relationship between these vectors, or you can say, hey, this is a collection of vectors. Given this collection of vectors, tell me whether the sentiment is positive or negative. Okay, you can do that as well. And there you're not really exploiting the sequential information. You just have a collection of word vectors, and you're just trying to say whether a sentiment is positive or negative. So you can do that. But here we'll mostly be interested in sequential information. Let me see where's the chat box so that I don't miss any questions. Okay, I got it. So okay, what are these other types of tasks? So one example is one-to-many. One-to-many, as the name implies, you give one input and you produce a sequence of output. And okay, and a very popular example is called image captioning, where a single image, one of the CIFAR10 images, or bigger, high resolution image is the input, and the output is actually a caption, a sequence of text, a sequence of words as the output. Okay. Now, there's of course the words cannot be jumbled up, right? Otherwise, it will not make a coherent caption. Similarly, the opposite, where you can give a sentence as an input and produce one thing as an output. And this is something that we've already seen before when we did the CNN based sentence classification. We were taking some sequential information into account because the words that appear, their embeddings were put one below the other in a matrix, and then we were doing a sliding, a sliding of the filters, and then doing some max pools and fully connected layers and all that. So we were taking sequential information into account. Okay, but here in this diagram, you'll see that there's a particular way in which I've drawn arrows, and these arrows actually correspond to the way RNN works. And I'm going to talk about RNN in the next slide. But this is an example. Okay, finding, for example, doing sentiment classification is an example where you might want to exploit sequential information. Okay. Of course, now you can have both, the combination of both multi-inputs and multi-outputs is exactly many-to-many. For example, here, the example is a machine translation, and this is something that you will try to work on in your assignment. And this is one of the key, I guess, sequence-to-sequence examples where there's a sequential input, which is let's say a sentence in English, and there's a sequential output, maybe a sentence in Chinese or sentence in French or whatever it is. And similarly, and the slight variation of this many-to-many is another version of many-to-many, where you don't wait till the end of the input to start producing outputs. Okay, so there's this delay between, hey, let's look at the whole sentence and then produce the new sentence in new language. Okay, you could do start producing outputs immediately when you get input. Okay, and that, for example, one of the examples that's written here is video classification, but it could be any, wherever you don't need to wait for the full input to start producing an output. Okay. So these are some examples. So now let's talk about the green stuff in the center. That's related. That's before we talk about the wiring of the green blocks in the center, we want to capture the idea of persistence, and this is basically the idea of how to capture temporal information. Okay, like we certainly have temporal information. What I'm saying next sentence is certainly related to what I said like 30 seconds ago, right? So we understand, and we generally understand the present given what we have seen in the past. Okay, what I've discussed in the past may give you information about what we are discussing next. For example, in the context of this session, right? Directly, in the sense that if you use the native instantiations of feed-forward neural networks or CNNs, they don't explicitly model persistence. Okay, they take an input, they produce an output, right? 1:1. They're not remembering, hey, what was the previous input for which I did a classification, or the previous input for which I did a prediction of, maybe some other type of prediction. So, for example, here, you can classify every scene, every frame in a movie or in a video. Output is fixed, okay, some classes, and number of layers, of course, is fixed because the CNN, whatever is number of layers is layers. But it's unclear how a CNN can use information from the previous scenes or the previous frames it has classified, right? So if you're reapplying classifier again and again and again, it's unclear how to use the previous classification outcome. Okay, and this makes sense for images. Of course, we know how to use previous information in when you're really working with just numeric data, right? We certainly have used time series models before. We can just add the previous data as extra features, and we can forward like that. But with images and text, it's unclear. And recurrent neural networks are one way to address this idea of persistence explicitly. Okay, so there's just one way. There are many ways to capture persistence. And in fact, next session, we'll look at, as I said, transformer architectures, which will also capture temporal information. So they also capture persistence. And we also know that in time series modeling, there are many, many methods to capture the idea of persistence. Okay, what happened, let's say the stock price went up, like 3 days ago, has some impact on what would be the stock price today, right? So we can capture that type of persistence with even traditional time series models. Okay, so with that background, let's talk about now the RNN building. So how does the RNN look like? We'll start with a top-down view. We'll look at the inputs, outputs, and at the block level, and then go inside the block. Okay. So let A represent a base network. Okay, what I mean is, just think of it as some function. Okay, when I say a base network, just some function. And as you can see in this diagram, this A has 2 inputs and 1 or 2 outputs. Let's say 2 outputs. In this diagram, there are 2 outputs. It's a function which takes 2 inputs and produces 2 outputs. Okay. Now, so if I had a function, so just think of, A is a function. A is a function taking, input 1, input 2, and it's producing output 1 and output 2, right? This is what it's doing. Now, what we're going to do is do a loop, which is as follows. We're going to take one of the outputs and plug it back as an input. Okay. Now, you're going to say, hey, what is going on with this picture here? There seems to be some circular computation. Okay, this is exactly, this is just a diagram. Okay, this doesn't really reflect the underlying computational graph. Okay, and so this is the diagram that people generally draw, when they want to draw a RNN or some sort of a recurrent architecture. Okay, so there's some input sequence of inputs, so that's why there's a subscript T here. So at the X, okay, there's some sequence of inputs that are coming in. There's some sequence of outputs that are being produced, and there's going to be some recurrent connection. Okay, and that actually does not correspond to a computational graph. As I said, the actual computational graph, this is a close approximation, which is called the unrolled diagram. Okay, the unrolled diagram is saying, hey, take x naught as an input at the beginning of the day, like at the beginning. There's no other input here. Okay, it's just like nothing or zeros, and that produces an output, and I produce another output. The second output is going to be fed to the next instantiation of the same computation block or the same function. Okay, new input, the previous block's output is going to produce a current output, and again a new input, which will be new output, which will be fed as input to the next block. So if you see here, I'm using the same letter A everywhere. Okay, which means that by which I'm trying to mean that I will use the same parameters in all these steps, or all these function applications. Okay, so let's call this theta. Then it's going to be the same parameter theta, and theta. So this is actually an RNN. So just think of RNN as, instead of layers, they are indexed by roughly time. Okay, it doesn't have a time, but some sequence index. Okay, and at every time index or sequence index, some operation is going on. Some couple of inputs, couple of outputs. Okay, and the function being used at each time step, whatever is the parameters, it's the same function being used at the subsequent time steps or subsequent sequence indices. Okay, so this is exactly, unlike a layered view that we had for CNNs and fully connected layers, here we have the time indexed view, and every time index we are doing one operation. Okay, that operation is hidden inside A. We'll talk about what is inside A. How are we getting 2 inputs? How are we getting 2 outputs? There's some small neural network in there, but modulo that, this is the computation that's happening inside an RNN. Whether it's an LSTM, whether it's some other RNN that you might have heard of, all of them typically will have a architecture like this. Okay, with the extra bells and whistles, we'll talk about bells and whistles later, extra variations, but this is the core. This is the most basic RNN diagram. This one is called the unrolled diagram, and generally people want to have a short form for this, so they just connect an input to output to an input. Okay, but that doesn't mean, that just means this, what's on the right side. Any questions at this point? Okay. Yeah.
So could you please explain it again? I'm confused.
Yeah. I mean, so at this point, everything should not be clearly because I haven't told you what A is. I just, for now, I've only told you that A, just think of A as a function. I mean, instead of, I could have used F, right? I mean, doesn't
Okay.
matter, A or F,
Okay.
some function which takes 2 inputs and produces 2 outputs. Okay, in fact, we'll later see that it's 2 outputs is also optional and all that. But anyway, some function which takes 2 inputs and 2 outputs. I've just wired it. If I think of that as like one of the computation, if you think of computational graphs, if I think of that as some huge node, then it's just doing this, right? So taking some input and producing 2 outputs. I'm just reusing the function again and again.
Okay. So the function is reused. I see that there is x naught till xt and h naught till ht.
Yeah.
So the x naughts are the inputs.
Yes. If I have a sequence of length, let's say 10 inputs, then x naught to x9, let's say, would be the inputs here, the ones below. And h naught to h, whatever, again, 9 could be outputs, but we may not care about all the outputs. Let's say, for example, whatever, even though the function a produced h naught, I don't care about it. Maybe I only care about the last one, whatever is that.
Okay.
It's just a, yeah.
Okay. And in the flow chart beside this, so what is the arrow doing there? So you're doing some recursive
Yeah, that's why this is called recurrent, because there's some for loop going on. So this is just a shorthand notation to show exactly what's happening on the right side. Okay. Instead of drawing the right side where every time step it's almost the same computation, right? It's exactly, if you just focus on each column here, like this column, this column, this column, this column, it's all exactly the same diagram, right?
Yeah.
So instead of drawing it several times, they've just put a one shorthand notation people use as a loop.
Yeah. That part I understood. So that meant that you're actually reusing the function. That's all.
Yes.
Got it.
Reuse the function. So this right hand side is called the unrolled diagram.
Okay.
And the name recurrent just means this use of reuse, right? So or this for loop here, basically this arrow.
Okay. Got it. So I was thinking that you're actually taking the output and giving back to the function and using it for the.
Yeah, that's exactly the point of this couple of slides was to say that we are not doing that. Okay, that's very that's like there's some circular logic going on right there. How can you give an output again as an input?
Yeah, exactly. Okay.
What happens?
Thank you.
Yeah, so this is actually the diagram. Okay, the one on the right side. So you can actually ignore the left side, but you'll see in many, if you look up online or in research papers, you'll see the diagram on the left side. Okay. So we want to avoid that. So we don't want the confusion. Okay. So now what I'm going to do is just try to open up this box A. But before that, let me just comment on a couple of things. So this, as I said, the sequential repetitive structure, of reusing A again and again, and of course, passing information from previous computations to next computations is exactly what you would do even even in time series. Somehow you would time series, like traditional models, you would somehow pass information from previous times to next times, right? For example, like you can have a model that says, hey, yt is equal to some 10 times yt minus 1 plus 9 times yt minus 2. You are using previous information to say something on next information. It's very similar to that. So basically, you can work with sequences. Okay. So for example, this is a sequence, right? This is the input sequence. So this input need not even be just numbers. Okay. Like in time series, one-dimensional time series, these are going to be just numbers. So that this can be an image in itself. This could be an image in itself. This could be an image in itself. For example, if you're doing video processing, or this could be a word vector. So input could be any numerical representation of any complex object. And we are in this class, since we are focusing more on more, I guess, exotic or more unstructured data like images and text, that's what I'm giving examples for. But you can certainly use RNNs for just stock, sales time series or stock price time series or whatever, returns time series, whatever it is. Okay. So those I did not give an example here, but those are the other examples. Okay. So as I said, at any stage, they accept input, give one or they accept potentially produce one or two outputs, and as I said earlier, they all this is the same function. Let's say you have trained an RNN, which just means that you have fixed the theta. Then it's the same function being applied like 10 times if you have a 10 length sequence. Okay, that's all. Just repeat that point. Now I'm gonna in the next, I guess, few minutes, I'm just gonna open the box A. Okay, so to show you a very simple, I mean, this is the original, I guess the smallest, okay, the cleanest recurrent neural network. Okay, we'll just see what is inside a box A, and since it's supposed to be a neural network, there's going to be a small, at least one layer, one fully connected layer type of thing inside. Okay, and we'll for that, let me just again introduce some minor notation. So an arrow represents a vector going from whatever left side to right side here, and this means concatenation, and this means copy. Okay, so if the same arrow is going to two locations, it's just like the vector is being input to two locations. And we have done this when we talk about computational graphs, we did, right? I mean, same input could go to two different locations in session 1. So, and this yellow box means a neural network layer. And when I say neural network layer, just think of it as a fully connected layer. Yellow box represents just a fully connected. It's going to be hidden because, of course, we don't, hidden, anything which is not input or output is basically hidden in this language. So it's going to be hidden layer. With that background, here is the inside details of this block A. Okay, so I'm just calling it vanilla RNN here. Vanilla, by just mean the plain. Okay, the simplest RNN you can have is the following. Okay, so the block, let's just focus on the block A. This is the block A. Okay, it's taking an input, as I said, as before, it's taking two inputs. Okay, and since we said, hey, if two things joining together means, what did it mean? Actually, concatenation, I guess. Yeah, concatenation. So if I have a, let's say, a two-dimensional vector here and a two-dimensional vector here I'll have a four-dimensional vector. Okay, 1, 2, 3, 4. That's going into a fully connected layer. Okay, and it says tanh over there, which means that fully connected layer with the tanh nonlinearity. Okay? I'm not telling you what so the input is going to be 4 dimensions to this fully connected layer. So X is a fully connected layer just means what? So WX plus B, right? And then tanh operation means, tanh. Okay? So this is what is happening. Okay. Now I didn't tell you what the output dimension is, but you can see that, hey, if the previous thing returned 2, then this should also be 2 because I'm just passing it to the next block, and that should be the input to the next A. So, and then, if the split just means a copy, right? So if I'm only producing one thing, one vector, and I'm just sending it to the next guy, next computation step, as well as outputting it now. So this is also 2 dimension. This is just an example to tell you what's inside that block A. Okay, so the only really a neural network is just this linear transformation with the extra nonlinearity added, and that's it. That's the recurrent neural network. So that's a building block. The block A is a building block for the RNN. I just chose some simple small numbers to show you how it looks like. And with this, you know one full RNN, actually. This is pretty much it. And I just want to stop, right after talking about this code base, because I mean, you have been working on assignment too, so this should be a little bit more familiar to you. So here is the same thing in code. Okay, so I'm doing it with NumPy, but basically you start with RNN, maybe extra NN dot module and all that, and then the init function will say, hey, there's a hidden vector h, okay, of some length, let's say 2. There's going to be a W and a bias. Okay? That W is going to be, let's say, 2 cross 4. And the bias is going to be 2-dimensional 2 cross 1. Okay? I'm just going back to this example. Okay, here I said there's a WX plus B, right? Yeah. So I'm just using those examples here. So there's going to be a hidden vector, a W and a bias. W and bias are going to be parameters which I have to tune. I'm also remembering the h. Okay, why am I remembering the h or the hidden output? Is because I'm going to call this function many times, so I need to remember the state, and this is one way to remember state in an object. Okay, you have to have a field that says, hey, what was the previous hidden value? Okay, so here's the step for this RNN, okay, which is that given a new input, I'll take the new input. Remember my previous hidden output. I'm gonna h stack as basically concatenate. Okay, and then I'm just going to do an np dot, which just means like once I do the concatenation, I'm just doing w h and x plus b. Okay, this is what I'm doing. I mean, I have to concatenate those two. And I'm applying a tanh operation. and I get a h, I'm just remembering that h. Okay, I'm just remembering that h here, and I'm also returning that h as an output. Okay. So this is how you'd call an RNN. If I instantiate an RNN with say 3, 4, 3 just means the hidden vector size. So instead of 3, let's say it's 2, and the input is also 2-dimensional. Then it's exactly what the running example we said earlier. Okay. So you just produce an xt, pass it to the RNN, you get a ht, and that's it. So RNN remembers the ht, and the next time you pass xt, it's going to remember its previous h, and concatenate and do this transformation, apply nonlinearity, and so on. Okay. So let me pause here. We'll talk about from this slide onwards next time. So this is just a simple implementation of an RNN. So let's actually come back to the picture. Okay. Again, as I said, once we have the parameters of the RNN, remember what are the parameters of the RNN? Just the W and B, right? With W and B, I can tell you everything what the function A should do. W, B, and tan h. Tan h is is just a function. So with W, B, and tan h, I can tell you exactly what, given 2 inputs to the A, I can produce 2 outputs from A, right? If I give you W, B, and tan h. Now what's happening? I'm taking xt. I'm taking my own previous. I just need to remember what was the previous h. H. I'm using h because it's a hidden output. Okay. Remember the previous h, take the current x. It's not just wx, but wh comma x. Okay. Wh and x are being linear transformed, and then tan h is being applied, and then that's being passed forward to um, um, the next computation of next computation, where again a 2-dimensional vector goes in, a 2-dimensional vector comes in from the input, that becomes a 4-dimensional vector, and then again the A operation gives me a 2-dimensional vector. Okay. Which is the h, and that's how it works. Any questions about the operation of how block A is performing? It should be fairly straightforward for some of you at least. But if you have questions, just let me know. And since we are running out of time, we ask questions even after I stop recording, as you wish. Any questions? Immediate questions I can answer before turning off the recording. Otherwise, I can turn off the recording and please stay back and ask questions as needed. Okay, so what I'll do is stop recording, and folks who want to please go ahead, and folks who have questions, please go ahead and ask. Let me stop recording.